it's my pleasure to have Massimo Franceschetti again here in Cassino, and he will talk about this intriguing topic that is electromagnetic and information theory. So thank you, Massimo.
Thank you, Donald. Thank you very much. I'm happy to be back here. I used to come often to Cassino, but I haven't been here for a couple of years. Nice to be back. Okay, I'm gonna give an overview of electromagnetics information theory. So let me start giving you the main idea behind it. So it's an idea that dates back a long time. If we look at the first issue, actually, of the IEEE Transactions on Information Theory, there was a paper by Dennis Gabor, and on this paper, Gabor argued that communication theory should be considered as a branch of physics, as it's really the objective of communicating information between two parties. In the middle, there is a physical channel, and that act of communication should be considered as a physical act, and therefore should be grounded on the discipline like physics. Of course, a lot have been going on since 1953, and most recently there has been a much renewed interest in joining these two fields. In fact, we believe that in communication theory there has been a lot of mathematical abstractions of the channel, but with today's technology there is a lot that can be gained for a more accurate description of the communication channel using physics, especially with new technologies that came about in the last 10 years or so. And this interest is testified by a number of activities that occur at the IEEE level. For example, there has been a special issue in the IEEE Transactions on Communications very recently on the topic of electromagnetic signal and information theory for communications. And in the works, there is a special issue of the Information Theory Society, and both Donald and I are involved into that as editors. That also is on the topic on electromagnetics and information theory. Coupled with this, at the IEEE level, there have been many special sessions and conferences on this topic. And so there is definitely interest, and is a very good field for graduate students to jump in if you are interested. So the idea is that you could have impact in studying both limits and design guidelines for new communication technologies, especially in the field, new field of holographic MIMO, where basically you are able to have almost complete control of the currents on an antenna, and therefore what you are generating is really a continuous signal. And so that's where electromagnetics and the signal analysis can provide a lot of insight into the communication process. Also in quantum communications, superdirectivity, molecular processes that are inherently continuous, and so on. So basically give limits on communications, what's achievable, what is not achievable, as well as design guidelines. Another field where I think that impact can be made using this idea of joining the two fields is not only communications, but also information extraction through remote sensing. There is a lot of literature there on the how to process the information coming from scattered data from objects through electromagnetic propagation, to give limits on imaging, radar, super resolutions, and things like that. Definitely, there is more interest right now in the communications aspects, but I think that another potential area is remote sensing as well. So with this motivation in mind, what we're going to do in this seminar is to explore two parallel roads to characterize the information content of an electromagnetic wave. The two parallel avenues are a mathematical one and a physical one. So let's start from the mathematical framework first. And again, a little bit of history. From the mathematical perspective, information was defined in the 50s by Shannon. And at the time also, the Soviet mathematician Andrei Kolmogorov was interested in characterizing from a mathematical perspective what is information and how this can be represented and communicated. And if you do a little bit of research, it's very interesting to look at the history. Actually, Kolmogorov attended one of the first IEEE symposiums on information theory and presented his way of representing information using functions, basically functional analysis. And he was very interested in Shannon's work that started that field. That's why he was at that symposium. And at the same time, Shannon was very well aware. He had presented his sampling theorem just a few years back. I think a sampling theorem is 1949, if I'm not mistaken. And he was aware that the sampling theorem was not completely rigorous. He gave an argument, but the epsilon and deltas, the fine mathematical details, were not worked out yet. And so he actually, at Bell Labs, he asked a group of mathematicians, Landau, Pollock, and Slepian, to look into this problem. And actually, I had the opportunity of meeting one of them, that is Landau. He's very old now. But he told me firsthand that Shannon asked them to look into that problem because he wanted to see how things can be made rigorous. And in fact, they wrote a series of papers, these three guys that are known as the famous Bell papers that came out of Bell Labs, to characterize the number of degrees of freedom of unlimited signals from a mathematical perspective, and made basically the results of the sampling theorem that we use in engineering rigorous from mathematical perspective. So that's a cool story. And actually, I want to start looking at the basic results of these Bell papers, the foundations. I will do that in a moment. First, I want to tell you that this mathematical road is parallel to a physical road, because the signals that we are working here are not arbitrary signals, but are the signals that are described by propagation of waves in electromagnetics. And there also we have, of course, a rich mathematical representation that's back, of course, to Maxwell, so much earlier than signal processing or information theory. And the thing is that by the physics, we know that whenever we generate a signal at the input of the system, that is typically the current distribution, currents in time and space, we receive the radiated signal, F, that is the image of the source through a propagation operator. The propagation operator is the Green's function that is described by Maxwell equations. So Maxwell theory puts properties on this operator, and therefore the signal that we measure here at the receiver is not arbitrary, but it has to satisfy some properties here. And these properties pose a limit on the amount of information or the type of waveform that you can measure at the output. So that's where the physics come in. So we'll have to use the mathematical theory, but then we'll also have to put some properties that come from the physics on the type of functions that we're going to deal with. And that's where the interesting thing comes when we put the two together. So let's start with the mathematical road first. So let's start easy with something that we are familiar with as undergraduates in engineering, actually, that is the representation of time frequency signals. So you have a signal f of t, in time. And of course, this is your electromagnetic signal, but for now, let's think about it as just a waveform. And you observe it over an interval P. And then you have the frequency representation of this signal that is f of omega. When you take the Fourier transform of this, you have a band-limited signal. You assume that you have a band-limited signal that is band-limited to the set Q. So you have a band-limited signal, and typically it's finite energy because we are able to generate signals that have finite energy. And finite energy in mathematical terms is translated in the requirement that the signal is square integrable. So the integral of the square of the signal is limited by a constant. So if you have such a signal, what is the amount of information that this signal carries? In the first approximation, we can say that the information can be represented by the degrees of freedom of the signal. What are these degrees of freedom? Degrees of freedom are the number of coefficients that we need to specify to generate the signal or to represent this signal at arbitrary precision. So what do I mean by that? If I take my signal and I try to approximate it using basis functions, some basis functions T of n here, and I use an n-dimensional representation of it, the error that I commit should be less than an arbitrary quantity epsilon whenever I have large number, a number of basis functions that is large enough, greater than n. Okay? So whenever n is greater than this n epsilon, that is the number of degrees of freedom, I am sure that the error is small enough, is smaller than epsilon. Okay? So if we take this to be the best possible approximation of f over all possible choices of basis functions for the worst possible signal. So we take the most difficult signal to approximate in the space of band-limited signals, and we take the best linear approximation of it. This error is called the Kolmogorov n width, and the number of functions such that the Kolmogorov n width is less than epsilon is the degrees of freedom. So it's how many real numbers you need to represent the signal if you are going to use the optimal representation for it. Okay, it's a little bit abstract. It's a little bit abstract concept, but the intuition is clear, right? It's the optimal subspace approximation of the signal. So that's the number of degrees of freedom. Is how many numbers you need to reconstruct the signal. So one thing that is important here is that you expect that the number of degrees of freedom depends on the level of approximation that you need. The more precise you want to be, the more functions you need, right? However, you would like to have a quote-unquote weak dependence on epsilon, so that the number of degrees of freedom is well defined as is a quote-unquote intrinsic features of the space. That means that you would like that up to first order, the degrees of freedom is a number that does not depend on epsilon too much. It depends on epsilon weakly. Okay? Because then you can say all band-limited signals have this number of degrees of freedom for arbitrary precision. And that is exactly what Slepian, Landau, and Pollack have shown. So this number of degrees of freedom can be computed, and you can show that the number of degrees of freedom is the bandwidth times the window of observation, the product of the two. And there is a pi here because this is the angular frequency. So that's why you have the pi, but it's basically time bandwidth product plus a little o, so a little bit that is really minuscule compared to omega t. It's really small. Little o is an order much weaker than omega t. As t goes to infinity, so as you widen your observation interval, this is the asymptotic expression. And the good thing here is that epsilon does not appear in the first order. So this number of degrees of freedom is up to first order independent of epsilon. Epsilon appears only as a pre-constant of this second order term. Okay, so that is what it means that is weakly dependent on epsilon, which also means that if you were to represent the number of degrees of freedom at the scale of t, it would be just omega t over pi, because this term disappears and it does not depend on epsilon at that scale. So the number of degrees of freedom of the waveform, band limited waveform, corresponds to the number of parallel channels available, because every real number can be considered like a channel of information that is that the waveform is communicating, and is given by the time bandwidth product. So that is the main result, and bear with me that there are, I think, 6 papers. The Bell papers is a collection of 5 or 6 papers, and I compressed the results to 1 slide. So, but that's essentially what they have shown there. And I have read them. I did read them. Now, there is now a m-dimensional generalization of this that is of interest to us, because our signal is an electromagnetic signal. It's not only a signal that varies in time, but electromagnetic signal also varies in space. So it's a space-time signal. So we need a function that is a function of many variables. In general, m variables. For example, in the case of electromagnetic signal, would be 4 variables: space, x, y, and t, and time, x, y, and z, and time t. So how do we generalize the result that we have seen before of the number of degrees of freedom to m-dimensional functions? Okay, so we have to generalize this picture. So we have an observation interval and the bandwidth interval. So where are we? Here. The observation now is going to be this blob, and we have 3 dimensions in space, and then ideally you have, I cannot really represent 4 dimensions, but you also have time. So imagine to move this in time. That's your observation interval. And then the band limitations set Q is basically if you transform the signal doing a multi-dimensional Fourier transform, you have to have a limited domain. So the coordinate x transforms into wx, wy, and wz, that are the components of the wave number in the 3 dimensions. And the time transforms into omega, and you have a band limited set over which the function is defined. And is observed over this set on the left, P. Now, to write the result on number of degrees of freedom, we have to remember that in time, we take the time bandwidth product, and we have this asymptotic with the little o, as the time observation interval was going to infinity. So the result was, as t goes to infinity, you have this asymptotic expression. To have something similar, we need to scale the observation set. How do we do that? Well, imagine to have this domain, this blob, and to inflate it to infinity. Well, by inflating, I mean you scale all coordinates. So you scale all coordinate x, y, z, and time. So in general, P is a constant set times a scaling factor beta. So every point has coordinates that scale by beta. And beta tends to infinity, so you grow that set. So as you do that, you can reveal the transition of the number of degrees of freedom. That is the generalization of the one we had before in 1 dimension. So again, if you plot the approximation error, and so that you want to visualize the number of degrees of freedom as a function of the number of functions that you use in the approximation interpolation, and you represent that at the scale of the beta to the n, at the scale asymptotically as beta tends to infinity. You see that you have the error that goes to 0 precisely at the precise value that is given by the measure of p prime times the measure of q divided by 2 pi to the n. So in one dimension, you have omega times t divided by pi. Here you have measure p, measure q divided by 2 pi to the n. Okay. So there you had omega was between minus omega and omega. Therefore, you had 2 omega times t divided by 2 pi. And here you have measure p, measure q divided by 2 pi to the n. So it's really the generalization of that. And so these curves here tend to a step function as beta grows, which means that this tail really becomes sharp, is a little O of 1 that tends to 0, and you get the exact phase transition point that gives you the number of degrees of freedom. And that becomes below epsilon at this value. And in fact, at the scale of beta to the m, does not depend on epsilon. So let's write this picture in mathematical form as a theorem. And that is a theorem of Landau that came after the Bell papers. Is a little bit later result. It is in the 70s. So the theorem says that if you take two sets, the function is band limited, is observed over a set p prime, but then you take your observation set p to be p prime inflated scale. Now, the number of degrees of freedom in terms defined by Kolmogorov and Wind, viewed as normalized by scale beta to the n, tends to the time bandwidth of the p prime and q product. These are a bad measure, the measure of p prime times measure q. So this also means that the number of degrees of freedom you can write as this product m p prime and q times beta to the n plus little o of beta to the n, where little o is really small compared to the first term, and this first term does not depend on epsilon. So epsilon is only in the little o. So really you have a generalized formula for the number of degrees of freedom that is always the size of the observation set times the size of the bandwidth of the support of the bandwidth support, both left and right, divided by 2 pi to the n. Okay, so this is the mathematical theory that I have up to this point. Really, really nice and clean. To familiarize a little bit more with this theory, we can apply that in one dimension to see how we can get the result that we are used to in signal analysis. Again, the set P is between minus t over 2 and t over 2. The set Q is between minus omega and omega. So what's the measure of P is just time interval t. The measure of Q is 2 omega, is the support in the frequency domain. So in one dimension, so if you apply the theorem, we have 2 omega multiplied by t divided by 2 pi, and you get omega t over pi as you scale the set t. Okay, and this coincides with basically the results that we have by the sampling theorem that says that this is the number of samples that you need when you have a time limited and band limited signal. Of course, it's much more rigorous because time limited and band limited signals do not exist mathematically, but you need to introduce these scalings. Okay, so that's 1D case. But now let's look for electromagnetic signals. What do we have? So we need to do more than one dimensions. We need to apply the mathematical theory in more than one dimension, so 2 and 3 dimensions, and in any given geometry of propagation. So what we are going to do is to start introducing the physics now a little bit and see where do we go. So to start introducing the physics, we'll work out first a 2-dimensional case, and we choose a circular geometry. So we choose propagation on this plane, and there are sources here that are going to be observed on this boundary, circular boundary, where the field propagates. And on this boundary, I have the sides R, but also an angular coordinate P that describes the position there. So really, for fixed at any given R, I have 2 coordinates: the angle and the time at which you observe the field. You observe the field this point, at this point, at this point, at a given time. And so you have representations of the function in time frequency, and then you can transform coordinates, time into frequency, and space into wave number. So this is the transformed waveform representation. So in this setting, let's go to this setting, and let's apply the Landau theorem to this physical setting. So we have to figure out what are the sets P and Q. So P is the observation set. So we're going to observe the signal between minus T/2 and T/2. So in an interval of time of size capital T. And the angle around this circle is going to be between minus pi and pi. That's our set P, this gray area here. How about our set Q? So for our set Q, we have the frequency varies between 0 and capital omega, because I'm assuming to radiate a band-limited signal, frequency omega. So time frequency goes from, the frequency goes between minus omega and omega. But how about the space? So the space constraint, I have a constraint on this wave number, here the transform of P, and I represent this constraint as this linear segment or line here. And this line has an equation W equal omega R over C. And this defines the limitation for the W component. So the gray area is the set Q. So why is that? Why by magic I can limit the set Q to this gray area? And the reason for that is the physics. So that's exactly where the physics come in. So remember when I told you that these functions cannot be arbitrary, but they must be constrained by the Maxwell equations. So they are the output of the Green's function operator that transforms the current into a field. And so for waveforms that satisfy Maxwell equations of propagation, you can look at the properties of the propagator operator, the Green's function, and study the propagator operator to figure out the limit on the wave number. And this is an old result that people in electromagnetics are very familiar with. It's the result of Massimo and Franceschetti in 1985 that have shown that the so-called spatial bandwidth, and so the spatial bandwidth is nothing else than the Y component of this gray area. So it's how much support the wave number W has. So the spatial bandwidth is omega R over C. Okay. So in in electromagnetic literature that is written as beta r, where beta is 2 pi over lambda, but it boils down to this expression, omega r over c. It's the same thing. Of course, this is asymptotic as for large radius. Okay, so that's how we obtain this this sort of double triangular shape. And now we can simply put things together, the physics and the math. And in this constrained environment by the physics, we are going to take the measure of P, the measure of Q, that amounts simply to compute the area here and the area here is an integral, and multiply the two and see what we get. So measure P is the area of the left domain, is 2 pi times t. Measure of Q, if you compute this area, is 2 omega squared r over c. And so when you take them together and you divide by 2 pi, 2 pi squared, you get omega t over pi times this expression here. And so you see that you can interpret this as the number of degrees of freedom that you have in time frequency that you had before, times a new number of degrees of freedom, that is the number of degrees of freedom in space that is given by this expression. And it depends on omega, because it depends on the wave, it's normalized by the wavelength. So it needs, dimensionally makes sense, it needs to depend on omega. So you have the product of two terms, and this is the expression of the number of degrees of freedom for band-limited signals. So if you want, you can consider this as the generalization of Bucci and Franceschetti result for a spectrum of frequencies, a spectrum of omega frequencies. Now there is a caveat, though. You have to take an appropriate scaling of the coordinates of each support. So this is a little bit technical, but I will spend just 1 minute to try to explain that. Remember that in the result, we need to scale. Remember when we had the balloon, the P set was growing. So technically, in Landau's theorem, you need the P set to grow to reach the concentration result of the number of degrees of freedom. In this case, we cannot grow the P set directly because we can grow time, but the angular observation domain is limited between minus pi and pi. So how can we go around that? There is a trick that we can do, is to observe that on this side Q, one thing that we could do is to keep P fixed and let omega grow, and then we scale Q. And but that would be a limit, that would be a number of degrees of freedom in the wide band regime for omega large. If we want a number of degrees of freedom for a fixed bandwidth signal, we can scale time, capital T, and then we scale the other coordinates here, R, that is the size of the radiating system. So we can scale R here to Y component, and capital T here is sort of a hybrid scaling. Okay? And I went through the Landau's theorem, and I have shown that the hybrid scaling works as well. So basically, Landau's proof works also if you do this hybrid scaling. Okay. In fact, it works even in more general scaling configurations, but that's what's important for us. So that's what appropriate scaling means. So we have to take capital T to go into infinity, and also R to go to infinity, and we can even take them at any rate that we wish. So we can take R go to infinity slowly and T fast, or the other way around. It's still okay, as long as both of them go to infinity. Okay, so that's for 2D. For 3D is same idea, just a little bit more mathematically heavy, but it's exactly the same idea. So 3D case, you have a sphere now rather than a circumference. So you have radius of the sphere, but you also have two angular coordinates, theta and phi. And so we have to generalize what we had before. Let's look at p first. You have theta and phi and time also. And so the observation set now is a solid angle and is of sides 4 pi. And then you can imagine to move this 4 pi over time over a t length. So you have 4 pi times t as measured p. And similarly, that double triangular or bow tie figure becomes a three-dimensional figure where you have W1 and W2 that are the pairs of theta and phi. And so both of them have omega I over c as their limitation. So it becomes this three-dimensional shape. And so if you compute the measure of this three-dimensional object, that's what you get. And then if you take the product of the two divided by 2 pi to the cube now, you get this expression. And you have, well, actually, it's better to rewrite this in a more convenient form that is subject to nicer interpretation. So if I just rearrange these terms here, I get to this expression over here in 3 dimensions, where compared to the 2 dimensions, we have something very symmetric. We have the time frequency degrees of freedom, omega t over pi, multiplied by the space degrees of freedom, that in 2D, where 2 pi r omega over 2 pi c, and in 3D, you have 4 pi r squared omega squared over 3c squared pi squared. So there is pretty symmetric. And you have the asymptotics as t goes to infinity and also r goes to infinity. So this is the number of space with number of degrees of freedom times the number of time frequency degrees of freedom. Now, if you forget about the time frequency degrees of freedom and you assume to radiate just one frequency, a single sinusoidal waveform, these expressions reduce to the expressions that are in the papers by Bucci and Franceschetti in the 80s for single frequency. For frequency band, that's what you get. So interesting. Both of them depends on the frequency bandwidth. Both this one, of course, depend on the bandwidth, omega t over pi, but also the spatial number of degrees of freedom depend on the bandwidth. And the reason for that is that at every single frequency, the number of spatial degrees of freedom depend on the wavelength. And so it's natural that then it need to depend on at each wavelength you describe a bandwidth. That's where you have the second dependency on the bandwidth. And in fact, if now you generalize this one step further and you say, let me now take a spectrum of frequencies minus omega omega, and let me modulate this with a carrier and put it at carrier frequency omega c for communication. Now the dependencies become the time frequency degrees of freedom times the spatial degrees of freedom that are again the area for pi r squared, depends on the carrier frequency square or inverse of carrier wavelength square. So that's another interesting thing. So for any fixed size system and transmission time, the number of degrees of freedom increases with the carrier frequency. Okay. So one thing that I want to mention is that these are all this is partial to results that I have been working on. So this is the framework I have been working on, but there are also other frameworks that are equally interesting. And in fact, other people have related results using a similar approach, but not exactly the same. Everybody has its own twist, but the idea is still to put together the physics and the mathematics. So in particular, of course, Donald has been very active since the beginning in this area. There is the group of Thomas Marzetta in New York that is working on these problems. Earlier papers, there are some early papers of my postdoc advisor, David Shea. There is a group in the field of optics, Miller, Stanford, that actually is working out pretty much the same results from using the theory of optics. Very interesting papers there. Okay, so there are quite a few groups that present similar results. So what I'm saying is that I have been naturally partial to my point of view, but there are others as well. And actually, I should mention also recently I've been looking at the papers of Gustafsson in Sweden. Is doing also related work with yet another point of view, but very similar results. So, and I don't have it in the list because I just started looking at these papers recently. Now, degrees of freedom is only one step. We can go further. Now that we have these techniques, I think that we can go beyond the degrees of freedom. And so the two ways to go beyond degrees of freedom most natural are to follow information theory, where degrees of freedom is the first question that Shannon asked his colleagues: how many dimensions do I have? But he developed a huge theory, and the caterpillars of his theory are entropy and capacity. So degrees of freedom for him is just a first step to discretize information. And once you have discretized information, you can use concepts like entropy and capacity to define it. And so how can we use the entropy concept? So what is entropy? Entropy is not only degrees of freedom where you represent the waveform using a discrete number of real numbers. Now you want to represent the waveform using bits. So you not only discretize the waveform using a finite number of basis functions, but now you also want to quantize the values so that you represent the waveform using bits, not real numbers. How can you do that? And so there are two ways of defining entropy that are basically equivalent. One is the Shannon way, but using probability theory and stochastic processes. His waveform is a stochastic process. Analogously, we can do it for general function using a notion known as Kolmogorov entropy, that is the natural deterministic equivalent of a Shannon entropy. And so you have, in this case, you have a waveform that, as we said, has a finite number of degrees of freedom, can be approximated by a finite number of basis functions. But now that you have a finite number of basis functions, you can see every coefficient here as defining a coordinate, a point in space. So a waveform is literally a point in any zero-dimensional space. And so a point, every point in this dashed disk, that dashed n-dimensional disk is a waveform. So every point in this disk is a waveform, is a possible waveform that we have. So the number of dimensions of the dashed disk is n0, is the number of degrees of freedom. and every waveform is a point. We have infinitely many of them, infinitely many waveform in that disk, so it seems that the information is infinite. But actually, we have a resolution constraint. If we pose a resolution constraint, we can define entropy. And this means that, suppose now that I cover this domain by smaller disks, and these smaller disks have radius epsilon, and I cover the whole space. So that this means that for any point that is in this disk, I can associate the center of a covering disk. And so this waveform is equivalent to this one, equivalent meaning within error epsilon. It's within distance epsilon. So the error is epsilon. So the number of covering spheres is called the covering number. It gives me basically a code book that I can use to represent these waveforms with error at most epsilon. With error at most epsilon. Therefore, the covering number gives me, if I take the logarithm base 2 of the covering number that I call Q, I get the number of bits that are used to represent that waveform, the number of bits that are used to represent the waveform. And so the covering number should be related to also to the number of degrees of freedom, because it depends on the number of dimensions. How can we relate the two? Well, intuitively, you can see that what you could do is to take the volume of the big, the dashed disk, divide by the volume of the little sphere, and that roughly gives you the covering number. And so if you do that, the volume is the square root of E, that is, E is the energy of the signal, that gives you the radius. To the power n0 is the number of degrees of freedom, because that's the number of dimensions, divided by epsilon to the n0. You take the logarithm, and you get n0 log square root of E over epsilon, and that should be roughly the number of bits that you require. And in fact, you can show that rigorously that this is correct by putting all the mathematical details. So you can characterize also not only the number of degrees of freedom, but also the entropy of the waveform. So that's one interesting extension. One more step that we can do is, well, why do you stop at epsilon? Epsilon is your measurement device limit, right? But if you take a physical perspective, you can ask, I want to make epsilon small, really, really small. Can I make epsilon arbitrarily small, where there must be some limit on how epsilon small can it be? So epsilon is really the resolution at which you observe your waveform. So at the end, the resolution will be in terms of photons, of quantums of energy. And so if you go in that direction, you could say, okay, then what will be the entropy when epsilon tends to 0? So quantum at the quantum level. And so that's another direction that you can do. You can impose quantum energy resolution limits and look at the entropy from a quantum perspective. And so if you do that, you get an interesting bound that is given by this expression that basically tells you that entropy or information is basically related to energy, it's basically energy and size of the system. And R is the size of the system. So the cool thing here is that this is a version of Bekenstein's bound in physics. Bekenstein found this bound. It's called the Bekenstein information bound. And if you look at the history of this bound, it has a long history. And originally, he proposed this bound using these black holes thermodynamics. You might have, I mean, if you are into these kind of things. There are a lot of divulgative books that tells you these stories that physicists work out. If I take a sphere that contains a certain amount of information, I throw it into a black hole, all that information that I had in that sphere disappears. Where does this information go? It must go somewhere. And so they say, okay, well, the black hole is actually getting a little bit larger. By the fact that the black hole gets larger, we can find the amount of information contained in that sphere. And they have all these kind of arguments, and they find this expression. Okay. Later, he worked on it again, and he also found it without using the black hole stuff. He also found it using only quantum indetermination principles. But the cool thing is here is that we can also find it using our rich history, that is Komogorov, Shannon, Landau, and all these people, introducing some basic quantum indeterminacy also there. So that's the thing. So that's in this paper. And so that's almost the last thing. I want to mention one more thing, and then I'm done. One more direction that one could go is entropy is one measure of information. Shannon also gave another measure of information, that is capacity. And so while entropy is approximating the signal using a finite number of bits, capacity is the notion of taking these bits, let them go through a channel with some error, and see how many bits can be communicated from point A and point B. When these bits are perturbed by the channel, you're basically taking a waveform, and then you are moving a little bit the waveform because of the noise in the channel, and you want to know how much information you can recover at the receiver. So that's the notion of capacity. And so you can also study that notion in our framework, where basically we have this nice pictorial representation where every waveform is the center of this shape, and each of these shapes represent the error that you add. And so when you receive all these shapes that are sort of overlapping because of the noise, and you want to characterize how many of these you can recover despite the overlap. So I'm not going to go into the details of this, but we have a paper on that as well about another notion that is capacity. Okay. These are some of my references. Again, I'm partial to my results here. Some of them are old papers with Donald and Fulvio as well. I have a book on the topic, and some additional references more from the application perspective. We looked at ways of utilizing these results for radio maps and also reconfigurable antenna arrays, work in progress. But these are the more application oriented, these are the more theory oriented. So with that, I conclude. I don't have a clock. I hope I am in time.
Yeah, you're perfect.
Okay. And if there are questions, we can discuss online or offline as you wish.
Thank you very much, Massimo. Very interesting. Any questions from the audience?